Hi everybody, welcome to today's Girls Computing League class. So today we are going to be going over chapter 19, 21, 22, 23, and if we have time, 24 and 24b. So we're going to start with the final type of loop, result-controlled loops. And so a result-control loop keeps looping until a computation has reached a particular goal without knowing exactly how long it will take. So that's opposed to a counting loop, which you know the number of iterations that would take. So it's like an instruction in a cookie recipe that says keep stirring until the ingredients are thoroughly blended. And in that case, you don't know how many times you have to stir, but you have to stir until a certain goal has been reached. So here's the question. If you put $1,000 in a bank at 5% annual compound interest, then how much will you have at the end of 1 year? The interest is paid once at the end of the year, so you will have $1,000 plus $1,000 times 0.05 or 5%. So you'll have $1,050. So here's the million-dollar question. How long does it take to reach $1 million? So take a guess. How long do you think it would take? Based on this table here, you can see that there's an increase of around $50 and it gets to $60. So how long do you think it would take to reach $1 million? So a really long time. So now we can write a $1 million program to calculate how long it will take. So you start the year with year 1, and you can see that you're adding another year's interest. So you're taking the number of dollars and then you're computing the amount of money you have in your bank, and then you're also incrementing the year. So year equals year plus 1. And then for dollars, then you would just take dollars times 1.05. And so what's interesting to consider is whether you would count what you count as the first year, if you would count the end of the year as your first year or the beginning of the year as your first year. So it really depends on what you want to be the end of the first year. So we're going to start with 0 because we're counting the first year as the end of the first year, not the beginning of the first year. And so we can see that it's not a counting loop because the loop is controlled by a calculation. And it's only finished when the goal is finished, not when a certain number of iterations have been performed. So why is this not a centennial controlled loop? So there's no data that is read in and checked for a centennial, so that's why it's not a centennial controlled loop. And so the gloomy news is how many years does it take to reach $1 million? 142. So you don't want to wait that long to get $1 million. So instead, you're going to put an extra amount of money at the end of every year. So how long will it take to reach $1 million at this rate? So we calculate the interest, and then we add in $1,000 and increment the year. So therefore, this is the next program, and it's slightly less gloomy because it takes 80 years to reach your goal. So now it only takes 80 years to reach $1 million. This is a considerable improvement. Can you wait that long? No. That's 80 years without chocolate chip cookies. So what if we choose a bank with a higher interest? So we're willing to wait for 40 years. So how high must the interest be? So one way to do this problem would be to try out various interest rates until you find one that works. So let's do that. So this program asks for a certain interest rate, calculates how much money will be in the account after 40 years. This loop isn't a result-controlled loop because you're setting the number of years or iterations to 40, and instead you're just looking at the output. So this is a counting loop, not a result-controlled loop. So we want to know how much money we will have at year 40. So year 40. And we're adding the interest, or the rate. So dollars equals dollars plus dollars times rate. So fill in the blanks, that's what we did, and here's the completed program. So the interest rate needs to be somewhere between 12 and 13%. So in the above dialog, the user keeps trying interest rates until one is found where the account reaches $1 million goals. In terms of computer programming, what is the user doing? The user is essentially acting like a result-controlled loop, continuing to iterate a process until a goal is reached, in this case, getting over $1 million. So we're essentially just gradually increasing the interest rate, so that's what we're going to do here. So here's a skeleton of the code, and you can see that there's just the definition of different variables, then there's a while loop, and in that you change the current rate, compute the dollars after 40 years at the current rate, and then it loops again to see if the dollars is less than 1,000. Less than $1 million. So if it is less than $1 million, then the loop continues because obviously the rate hasn't been reached yet. But then once the amount of dollars does go over $1 million, then it exits the loop and then goes to the print statement. So in the skeleton program above, does not have the code for the part that says compute the dollars after 40 years at the current rate. How do you expect that this will be done? So that's what I just explained. So this is a dollars calculation from the previous program, and it's slightly modified. And so we're going to copy paste the dollars calculation into down here. And that's essentially what we have to do. So that's the new program. When you run it, you can see that you will have at 12.6% interest, you will have a little over $1 million. And so again, this is an example of floating point inaccuracy. The number should be 12.6, but instead it's 12.6000, a bunch of zeros and a 9. And so that's just a demonstration of the floating point inaccuracies. So why is this statement from the program important? Dollars equals initial amount. Well, it's important because if we don't reset the dollars every time the loop runs, then we will continually be incrementing like the amount of money. So therefore, even at a low interest rate, we might think that we have reached the correct amount of interest, but in reality, there isn't actually that much amount of money. You're just compounding it from loop run to loop run. So here's a flowchart of this program, and so you can see that you start by defining your variables. So in this situation, it would be that you have an initial amount of 1,000. You have $0, so that's the amount after 40 years because you haven't calculated yet, and you have a negative rate, meaning so that we can check the rate starting with rate equals 0. Then the while loop checks if the amount of money is less than $1 million. So if it's false, then it just prints the results and the program ends. So that means that we have reached our interest goal. But if the amount of dollars is less than $1 million, then we will calculate the amount of money with the current rate. So the rate is incremented. The year starts with the year 1. And then we have another while loop. Instead, this one's a counting loop. So we count the number of years till 40 and calculate the amount of money you would have in your bank account. So does rate keep increasing as the program runs? Yes. So the job of the outer loop is to keep incrementing rate every time the inner loop runs. So here's some debugging practice, and so the way that the variable rate is initialized and then immediately incremented is awkward. So here's a buggy program that does it in a different way. So we start at rate 0, and then we increment the rate later. So is there a bug with this program? And the answer is actually that there is a bug. So Essentially, when you can, in the program, you can see that, let's say you get after you finish this part of the loop, you have gotten the correct rate. But then when you finish the outer loop, the rate is incremented. So the rate that is printed will be 0.001 off of the actual rate that meets the $1 million threshold. So the answer, the println at the end should be changed to rate minus 0.001 to fix this inaccuracy. So now we're going to be talking about Newton's method. So we've talked about the different libraries in Java and how java.lang.math contains the square root function and many other functions like sine, cosine, and absolute value. And so the functions in this library have been carefully written and tested by programmers who are experts in numerical analysis. And so let's investigate how the square root function could be written. So Newton's method of computing the square root of a number n is to first make a guess and then keep improving that guess to get a better guess. And at one point you would get very infinitely close to the actual answer. So here's the guess improvement process. There's a formula. New guess equals n divided by 2 times old guess plus old guess divided by 2. The reason that this works is actually explained in calculus, but we're just going to be using the formula. So let's say that we want the square root of n to be 3. The square root of n equals 3. So the first guess, you can always just start with 1. So the next guess after 1 would be 2. And then the next guess after that would be 1.5, and after that 1.73214, and then after that 1.73205, and then you keep going. And so it's just like by guessing more, you're getting closer and closer to the actual value. So why not keep looping until the results are exactly correct? Because we're doing floating point arithmetic, the guess is never going to be exactly correct. It's going to be close. And so with a fixed number of bits, there's always going to be a small error. So we have to decide what type of error is negligible and what type of error is not negligible, aka significant. So in this case, we have to decide a number for almost. In this case, we're going to be taking the absolute value of a number, meaning the absolute difference, and then we're going to make sure that it's almost 0. So the difference between the old guess and the improved guess. If there's a very small difference between the old guess and the new guess, that means that we're really close to the actual answer. So what is 0 point, a bunch of zeros followed by 1 in scientific notation? It's actually 1.0 times 10 to the negative 14th. So now we're going to be doing the skeleton of the square root program. So here is the skeleton with the loop ending condition translated from math into Java. The absolute value of a double is calculated by math.absolute and then double. And so the skeleton contains the result controlled loop. And so all you need to do is fill in the calculation part. And we can do this with a single assignment statement. So we have the formula for updating the guess. And so all you have to do is just update the guess. And so we can just use the formula. So here's the formula. And so we have our small value, and then n is the value we're taking the square root of, and guess is the guess. So essentially we have to create a new variable. So we can create a double new guess equals and we always have to make sure we're doing floating point and keeping everything in floating point. So if we wanted more accuracy than what is possible with double precision variables, what might happen? So what would happen if small value were 1.0 times 10 to the negative 21st? So the answer might be achieved, but if it cannot, the loop will go on forever. So you might get lucky and accidentally reach the goal, or the loop might just go on forever. So an improvement to the program would be nice if the user could enter a number for which the square root is computed. So basically we're asking the user to enter n. So here's a program as it currently stands. And so where can we put this fragment so that the user would be able to enter a value for n? So we could put it right here. And we can also change it so that we're not defining what n is, rather we're just creating a variable n but not giving it a value. So it doesn't hurt to initialize n in the declaration, but it might confuse the reader of the program, so it's better to just create the variable but not actually assign it any value. So what would happen if the user entered a negative number? Well, you can't take the square root of a negative number, so the loop would be unable to compute it and would run forever. So there are several ways in which you can handle defective user input, and so one would be to check the value that the user has entered, and if it's okay, then we can execute the loop, and otherwise we can run an error message to the screen and end the program. So here's a revised program with some blanks. So it's exactly almost the same as the previous program, except we have a few blanks where we can handle what to do with user input. So let's say we can have an if-else statement. So we can say if n is less than 0, greater than or equal to 0, sorry, then we can run the square root program. But else, then we can print out that the input is invalid. So will the program work if a user enters a 0? Yes, because 0 has a square root, which is 0. But due to floating point inaccuracy, the number that will actually be calculated is not exactly 0. So suggest a few other values for which the program could be tested. We can always try 1.0 because the square root is exactly the same, so the special case might confuse the program. Also, very large numbers could be confusing for the program, and so an initial guess of 1.0 might be too small or might just not work. So it's important to consider cases like that when you're testing a program. So that's the end of chapter 19. And so now we are going to be doing chapter 21, which is files and file output. And so files are extremely useful because sometimes you don't want the user to always enter in your data. Sometimes you want to get your data from a file or another source. So what is a file? So try to think of a one-sentence definition. So a file is a semi-permanent named collection of information. So semi-permanent means that your files can be deleted and they can also be stored. So currently files are stored on a magnetic disk where no matter, you can leave them there for dormant for many years when the computer is off and you would still be able to retrieve them. But the semi part comes in when you can delete the files, so they aren't permanent. And so also files are named so that programs and other applications can find the file when it is needed. So Microsoft Word, Microsoft Windows files look like this: mydata.txt, program1. Program1.class, doom.exe. So we can see that we have a text file, a Java file, a class file, and an executable file. And so files are also collections of information. So the purpose of a file is to store a collection of related information, such as word processing documents, a program, source file, a spreadsheet, or a database. And conceptually, this is what a file is. And so a file can be implemented in many ways. So you can have parts of your hard disk on your computer. You can have like a DVD, and that's a file. You can have parts of a magnetic tape. And there are many different other ways. So is there another way other than files for a computer system to keep information semi-permanently? No, there's only one way for computers to be able to semi-permanently store data, and that is a file. So, thought question: how is information represented in a file? Analog form, binary form, special forms? Everything is always in binary form. Like 99% of the time, everything your computer is doing is in binary. That's because it is efficient for your computer, and it's also just simpler, and a lot of things can be stored in binary despite how simple it is. So information in a computer system is represented in binary form. How bits are implemented depends on what type of file it is. Like if you had a JPEG file, which is like an image, that would be stored differently and encoded differently than if we had like a text file, for example. And so in magnetic storage media, such as hard disks or tape, the bits are encoded using patterns of magnetization on the strips. But optical storage media, such as CDs or DVDs, the little grooves engraved into the CD or DVD actually encode the data through patterns of light reflection, so that's very interesting. And so there are 4 advantages of binary, and so that's why everything in computers is in binary. So the 4 major advantages are that it's simple and it's unambiguous, meaning that a 1 means a 1 and a 0 means a 0. There's no intermediates. Flawless copies can be made because numbers can be directly copied. And anything that can be represented in symbols can be represented with patterns of bits. And so the last advantage means that a file that can contain any type of information, especially even information that's represented by symbols, such as numbers, characters, images, audio, bytecodes, many other types. So can a file hold any type of information that can be held in a main memory? Yes. So files essentially are the hardware, are like they can store anything. And so as far as the hardware of a computer system is concerned, all of the files look alike. And when the file is actually read, then they're translated into something meaningful. And when a file is written, the hardware accepts bytes from the program and saves them as part of the file. So this is where the input-output comes in I/O, because you can input from a file to a program, or you can output from a program to a file. So here's a question. The program Notepad reads and writes text files, but cannot deal with Microsoft Word files. Does this mean that those files are fundamentally different? No. At the hardware level, like I said before, all of the files are just collection of bytes, so they mean the same thing. But Notepad just cannot interpret the bytes intended for Microsoft Word. Like, they don't mean anything. It's like trying to have an English-speaking person interpret and read French, even though they're mostly the same characters. The words just don't have the same meanings. And so Notepad is written to read and write text files. So a text file contains bytes that represent characters, all the letters, uppercase and lowercase, all the numbers, the space, punctuation, and a few control characters that we've already seen before, like /n, /t. So text files are the easiest type of files for a program to deal with, And so the next few chapters will be dealing with these text files. So what type of file is used for Java source files? Text files. So text files you can open in Notepad, and so that's also very convenient. So Java programs can be written to deal with any type of file, but it is very easy, a lot easier, to write programs that do input and output with text files. So have your programs so far been doing input and output of text? Yes, they have, just not with files. You've been taking input from your keyboard and outputting to a monitor, but now we're going to be switching to learn how to do this with a file, taking input from a certain file and outputting to a certain file. So essentially what we are doing is we are redirecting the output. So the command line interface of most operating systems supports file redirection. And so this works for Windows operating systems and Unix and also Mac OS. And so the program that sends its output to the monitor can send its output to a file using output redirection. So say that you have a program called hello.java that writes hello world to the monitor. Here's how the program usually works, and this is command prompt. So without making any changes to the program and without recompiling, you can just do this. In command prompt, you can just type this instead, and this command creates a file .output.txt and puts the output of that program into that file. So then you can access the file and see what it says, and it says hello world, which makes sense since that's what the program outputted. So can you use Notepad to edit output.txt? Yes, because the ending.txt signifies that this file is a text file, and so once it's created as a text file, it can be read as a text file by any type of program that is made to read text files. So file redirection is a feature of an operating system and is part of the command line interface, but it's not exactly a feature of Java. And so file redirection can be used with any program that writes to the monitor. So for example, the DOS command dir, it's a directory, so you can essentially navigate to a folder and see all the files in that folder, or and like look through the different other folders and stuff like that. So you can send characters to a file, and you can type out the contents of a new file by doing this. And so these are just commands for command prompt that are useful. So if there's already a file named stuff.txt, what happens if you do that? The file gets overwritten. So you have to be very careful to name your file something meaningful and something you don't use for multiple programs so that you don't accidentally write over a file you didn't mean to. So one way to send the output of a program to a printer is to redirect its output to the text file. So instead of printing to your monitor, it would print to a certain text file. And then you can open this text file with Notepad or any other editor. And then you can use the print command and see what's exactly in the file. So here's an example of the hello.java that prints hello world, and it can be copied to a source file and run to practice. So after all of the above commands have been executed, what happens to the file called output.txt? Nothing. So before, at the beginning when we were learning how Java works, I told you that when programs are run, nothing gets stored again, so that each iteration of the program is its own unique iteration and that there's no dependence from previous runs of the same program. But in this case, when you're editing an external document, like a text file that you're adding or writing to, once the program is finished, nothing happens to it. It doesn't get deleted. It just stays there. So now we're going to be doing a discount program, and so this program has a list price, a discount, and then you calculate the discount price. So this is slightly more realistic, and it counts the discounted price of an item given the list price and the percentage discount. So there's an example of the normal operation of the program. But here's the question. Can the output of this program be redirected to a file? Answer is yes. It's a little awkward though, because the user prompts the program and gives it input. So the computed answer should be printed out on the monitor for the user to see, but should also be sent to the text output file for storage. So it's kind of like a receipt. And so here's an example of redirecting the output of this file. So notice that the user does not see any prompts because they have been sent to the output file. So it's kind of awkward because the user sees half the dialogue, but the other half goes to the file. So it would be better if you could have the dialogue on both the file and the monitor. So would it be useful if there were a way to send some output to a monitor even when redirection is being used? And the answer to that question is yes. So here's a modified program. So we're using the standard error output stream for this, and so characters are sent to a standard error that appears on the monitor, and that's even when the output is redirected to a disk file. And so you know how before we would write system.out.println? That means it's printing to output monitor, and so we're still going to be using the system.out.println, and the only difference is that we're also going to be using that system.err.println, which is printing to a disk file. It's a standard error output stream. And then the standard output stream will be used as well. So can the user pick any file name for the redirected output? The answer is yes, but like I said, be very careful about destroying files that you actually need. So here's a run of the modified program. So you can see that not only does the data get printed to the monitor, but it also gets taken to another file. So what happened to the previous version of the file discount.out in the current subdirectory? It got replaced with the new one. So every time you run a program and you don't prompt the user for a new file name, your files will continually keep getting deleted. So you just have to make sure that you're constantly either changing or renaming or doing something to see that you don't lose data if it's valuable to you. So now we're going to be talking about concatenation of output to a file. So sometimes you want to run a program several times and you want the output to go to a single file, but you want every time to print in the same document, not rewrite the document, and so that's called concatenation of the output to a file. So instead of using the single like greater than sign, we're going to use two of them. It means concatenation, so it just gets added on instead of replaced. So after all the above has been done, what would be the result of the command printing discount.out? So the result of the command would be that the previous file would be totally replaced and there would be new output in that file. And so that's exactly what we expect to happen if we're rewriting, not concatenating a file. So that's the end of chapter 21. Does anyone have any questions? Okay, sweet. So now we're going to be doing chapter 22, which is reading data from a file. So before we were talking about output to a file, so now we're going to be talking about reading data from a file. So the previous chapter discussed text files and writing text files. So where has the data from our previous programs come from? Mostly from a keyboard. So we've been inputting data from a keyboard into the program. But this time, we're going to be learning how to take that data from a file and use it as input instead of writing for output. So a program that reads input from the keyboard can also read input from a text file. So it's called input redirection, just like output redirection. And it's a feature of the command line interface of many operating systems. So let's say you have a program named echo.java, and you're reading characters from the keyboard and just echoing them to the monitor. Here's how the program usually works. Without making any changes, the input can be connected to a disk file. So you can see that before we were using the greater than sign, and now we're going to be using the less than sign. So the flow, you can see, it's kind of like an array. There's a flow from the input text file to the program. Before, it was from the program to the text file. So that makes sense if you think about the flow of data. So is input redirection a feature of Java or a feature of the operating system? And the answer is that it's a feature of the operating system. So it's inborn in many, if not all, computers. So you can write a program just like this, and it can use any type of file as input, but we're only talking about input from text files. And so this example program reads input from the keyboard. And so here's how it usually works. So we're prompting for the input, and then we're printing. This came from the keyboard. The program processes it and prints out the exact same statement. This came from the keyboard. So how many lines of text does the program read? Just one, because we're just using, we're just prompting for one next line. We're not waiting for more lines of information. So the program will not read any more data than it has been written to deal with. So even if there were multiple lines of data, it would only deal with the first line of data. And so, of course, the program could be written to read more than one line of data. And so here's an example. We have our input file, which has 3 lines, saying this is the first line, this is line 2, and this is the last line. And so the above program that we saw before only reads the first line, so we'll only print that this is line 1 of the program. So we see that there are 3 lines in the input file, and that the program is only written to read with 1, so we need the program to read multiple lines, aka in this case 3. So sometimes a file you wish to use for data for input starts with a blank line, and so that means that the first few characters of the file are the control characters, the invisible characters that are controlling formatting, such as new lines, tabs, etc., new paragraphs. And so you can make a file like this with the text editor by hitting Enter and then starting to type instead of just typing. So you have a blank character at the beginning, or like the first line is blank. And so we're going to see there's input redirection from the input file to Java Echo. And so essentially the first line containing only the end of line characters is all that is read in. So essentially nothing will be printed to the monitor. And so it'll look like the program isn't working, but in reality it is working. There's just a bug in your program. So to read 5 lines from a file, how many times must the scan the next line method be executed? 5 times. So as many times as you need to read in, then that's how many times you have to scan in the next line of input. So here's an example of an input loop in code. And so we can use a loop to execute scan the next line and the required number of times. And so the above program reads and echoes the first 5 lines of a file. And so this is exactly what we programmed the program to do. And so here's a program working with an input file. And so here's the input. It's in line 1, line 2, line 3, line 4. This is the last line. And so that's essentially what was in the document, and so that's, or the notepad file, and that's exactly what's printed by the Java program. And so here's the thought question. How would you send the output of this program to another file? So we would just use output redirection. So we've been using input and output redirection, but now we will start to use them conjoined, so together. And so redirecting both input and output. So input and output redirection can be used simultaneously. So here's an example of this program. So we have line 1, line 2, line 3, line 4, line 5. And so it doesn't matter the order of the command, and we just need to make sure that the arrows are pointing the correct way and that we are getting the input from the correct place and we're putting the output to the correct place. And so here's a thought question. Can you use redirection to send output to 2 disk files at the same time? And the answer is no. You can only input and output to one place at one time. So here's numeric input. So we've been dealing a lot with numeric input in all of the different programs that we have written, especially since we're doing a lot of number processing. And so we're going to be continuing to see numeric input, except now from a different source. So the reading and numeric input is exactly the same. We're taking a scanner and reading the next int. So this is exactly like the old programs you've seen before, scan on next int. So why are there parentheses around number A plus number B? It's because we want it to be evaluated, not just printed. So if we didn't put the parentheses around the A and the B, then we would see it would just print the number and the other number. It wouldn't actually add them. So we just have to remember that if we want to actually have something add together or be processed before the entire string, we need to put parentheses around it so it'll be evaluated first. So here's the input file for the sum program. So we have a 12 and a 7. And so you have to make sure that the input file cannot contain any characters that are not part of an integer. So you can also use the plus and the minus, but the numbers must be separated by the plus and the minus can be used because they are part of a number, and the numbers have to be separated by some sort of space or blank to represent that they are different numbers. And so here's an input file. So will this input file work correctly? And the answer was that the program will run without complaint and add the first 2 numbers, but it won't do anything with the second 2 numbers because we haven't told it to do anything with the second 2 numbers. And so let's say you have a file containing 100 integers, 1 per line. So you want to add them all up, but you don't want to write the add statement like 100 times. So this is where counting while loops are very useful because we can add up a large sum or quantity of numbers without having to write the same statement so many times. So we're going to start with int sum, and so the additive identity is 0, so we're going to start with 0. And then the count, we start the counter at 1 or 0 depending on what you want. So I like to start at 1, and then here I have less than or equal to 100. If I started with count equals 0, then I would just have a less than. And so now we're going to be printing enter a number. And then we are going to be adding the sum and incrementing the count. So in this case, we're still prompting a user to enter it as opposed to a file, because you can see that the scanner is taking the argument of system.in, which is the input from a person. And so we have sum equals, now we have to add up the sum. So we just got a number called value, so sum equals sum plus value. Count equals count plus 1. So here's the complete program. And if you run this program, you have to enter 100 integers, which is really tedious. So for testing purposes, we can just change 100 to a smaller number that is more manageable and test it out that way. So let's say you have a file of 100 integers and you run a program by doing this. What will the user see on the monitor? And the user will see something like this: enter number, enter number, enter a number, enter a number, enter a number, and it'll go on 100 times. And then we'll see a grand total. So 100 useless prompts is irritating. So we don't need to prompt the user to enter something because we're getting the input from a file. So programs that read from a file don't need prompts, so we can just comment out that line. And so we'll need a data file of 100 integers, so this is really easy to do. So we can just enter a line of 10 numbers and then copy paste them, make 9 duplicates, and you have 100 numbers. So what happens if there are fewer integers in the file than the program needs? So we have to try it and see. So the system will not mistakenly think that everything has worked correctly, and in this case it will give you an error saying that there is no more input. So that was chapter 22. Now we're going to be going on to chapter 23. Does anyone have any questions? Okay, so now we're going to be talking about scanner and print streams. So from before, we have been taking input and output from just the command prompt, as opposed to not using command prompt and writing the actual program to take the input from a specific file. So that's what we're going to be learning now. So in our program so far, what input stream has been used with scanner? We've said scanner scan equals new scanner system.in. So we're using the standard input, which is system.in. And so here's the diagram of input-output streams from maybe the first or second chapter. And so we can see that there's an input stream of characters, and the scanner reads it, converts it to a number, and then there's some processing in this case that the number is squared. And that numeric data is taken to the outprint statement, and it is system.out is processing it and making it a stream of characters that exits. So this is the same basic outline for basically all the input-output streams we're going to be seeing. And so we're going to see, could the characters of an input stream come from a disk file? And yes, and that's what's done with input redirection. So we're taking, instead from a person or someone manually entering it from the keyboard, we're taking it from a disk file, mydata.txt. So with file input redirection, a disk file is connected to the standard input stream using a scanner object. And so you can construct a scanner object that connects to a disk file. So the scanner can take multiple arguments. So when we were talking about before how methods take a value and then they use that value to process it and then they output a value. So scanner objects that when they're created can take an argument of either like system.in, so which is like the input streams, or it can also take a file object. And so a file object is exactly what you would think it is. It connects to a file. So essentially, by creating a file object, you're creating a way for the program to access the file. And by using the scanner object, it's like the road which you can use to access the file. So in this case, you would write file equals new file, and then the name of the file as a string, and then you would create a scanner scan equals new scanner, and in the parentheses, instead of putting system.in, we would put file. And so these statements create a file object, and then we're creating a scanner object that uses the file object. So must the disk file that is used with the scanner be a text file? It has to be, because scanner can only take an input of characters and convert them to different types of data. So for example, if we put a JPEG or some other type of image, or like an audio file, it wouldn't work. So here's a program with disk input. So it's like the same square program that we saw modeled a few slides ago. And so here's a program with the program fragments we were talking about before. So we can see here that the program matches the picture. And so is it possible that mydata.txt might not exist? Oh yeah, it is of course possible that we forgot to create the file or we typoed or something and the file does not exist. In this case, the program will not just continue like everything was okay. It will throw an exception. And so just to review, an exception essentially is an error and it prints out a stack trace. And so the stack trace is very important in helping you determine what exactly went wrong, which line it went wrong, and what happened. And so you can see here that it says exception in thread main. So in your main method, there's something wrong, and it says java.io.file not found exception. So this is one of the very self-explanatory exceptions saying that your file was not found. So either you have to define the file, or you typoed and you weren't referring to the correct file, or something along those lines. So essentially, this is one example of an I/O exception or an input-output exception. And so there are many other input-output exceptions. There could be like a mismatch error, which is, for example, we talked about a while ago, saying how you could, if you're asking, for example, for an integer, and if I put characters, like if I write my name instead of giving you a number, then that's a mismatch exception because it's not the same type we were looking for, and so it's stuff like that. And so later chapters we're going to talk about what to do with these exceptions, but for now all we need to know is that these exceptions are pointing us and telling us that something is wrong. So is this program, just reading one integer from a file, really useful? Not really. So most files contain a great deal of data, and that's why we use the files. If we only had one integer to enter, it would probably be more practical to just prompt the user for it, but since we're entering a large deal of numbers, then it is probably most efficient for us to look for multiple numbers or process multiple numbers if we're going to be using a file. So here's a question. Does this program require a specific number of integers in the input file? No, it's a centennial controlled loop, so it's just the end of the file or something that can be read as an integer. So for example, the following could be the contents of the input file, and it would just go to the end, 67. So would the following contents of this input file work? It would work because it would get to rats, read it in, and see, oh, it's not an integer, therefore we have reached the end, or we have reached what is perceived at the end. So now we're going to be talking about a very important method. It's called the has-next methods. And so these methods are essentially asking the question, they're essentially asking the question, do we have another input? So has-next is just checking, is there any input next in the file or the scanner? And then has-next double is seeing, is there another double? And then is there another float? Is there another integer? Is there another line? And is there another long? So does calling a has-next method consume any data from the file? No. It's like a peek. So you're peeking at the next data point, but you're not actually viewing it. So the thing is, once you get the next integer or the next data point, you can't go backwards. So the has-next allows us to see if the data point exists and then decide to process it or not process it. So here's the question. Would a file containing the following be correctly processed by this program? So we can see that this program has a while loop and an if statement inside of the while loop. And so the while loop is essentially saying just keep, it's a centennial controlled loop, so it just keeps going until the end of the program or there's more data to process. if there's no more data to process. And then inside, we're seeing is it an integer? If yes, then let's process the data. If it's not an integer, let's just skip it and go to the next one. So would a file containing the following be correctly processed? And yes, because it has the ability to skip over those those characters and just go for the numbers. So it would be nice to allow the user to give the file name, but we already have a scanner, right? But we can always make another scanner. So that's the beauty about objects, is that we can make as many objects as we want from a class. So we can have two scanners. One scanner that reads the input from a file, and one scanner that tells us what the file name is. And so that is the part in blue. And so we definitely will review this next class, but this is just, I guess, a peek at what is going to be next. So essentially, the user is being prompted for a file name and can enter a file name. And using that file name, a file object is created, and then the file has a connected scanner that is created, and then we process the data just like before. So if the user enters a name, a file does not exist, will the program end gracefully? And the answer is no, there will be an error. We will get the same error, file not found exception. So that is not gracefully. So we can handle the exception or process it and end gracefully, as it is eloquently put, but this will be covered in a later chapter. So right now we're just going to be focusing on that. Let's take the hypothetical situation that the file does exist and all the input data is correct. So here's an example run, and so there's just a bunch of squares and it all works well. So is it ever useful to send output to a disk file? And yes, what if you want to store a certain amount of data in a specific safer place that is more permanent? So in this example, we will be using a print stream, and so print streams are very valuable because we can use them to print data to different files, and so it's used for character output to a text file. So it's a little more specific than just taking output and putting it into a file. And so it does create a text file, so that means that you'll be able to open it in Notebook or some other text file processing application and be able to view and edit it. And so essentially almost the same thing is happening, except instead of creating a scanner object, we're creating a print stream object. And so a print stream is exactly what it sounds like. It prints a stream of characters. So we're creating a file telling the print stream where to access the data, and then we're creating a print stream to link our program with that file. And so so instead of saying system.out.println, we're doing print.println because print is a print stream. And so when we do system.out.println, we're using the standard output prints, the output stream. So in this case, we're just redirecting it to print to a different print stream. So in this case, it's to the file. And so would it be possible to still use system.out.println? Like at the bottom of this program? Yes, of course it is. And so here's a question. Could the type command be used in the Windows command prompt to see the contents of this file? So yes, because it's an ordinary text file, like I said, we can open it and edit it and view it. And so the print method of print stream sends the characters referenced by S to the output stream. And so that's essentially what I was saying before. We're taking whatever the program you want the program to print, and then you're sending it to the print stream, and the print stream is sending it to the output. So it's sending it into a text file. And so let's say we want to improve on this program, and so we want to ask the user for the output file name. And so in this case, it's the exact same way as the name of the input file with scanner. So we're going to just be doing system.out.println and then using a scanner to get the name of the file, and then we're printing it out. And this is the end of the chapter, so we're almost done. So we have to prepare the output file, so that's printing out the output file name, and then scanning what the next user has put and has inputted, and then we're going to save that string as output file name, and then we're going to create a file with that name and then print that file. So how would you create a program that adds up all the integers in a file of text integers? So we can just modify the example program, and so that is your project for next class, to modify the example program to do just that. And so that's the end of chapter 23, and so we're right on schedule. On your own, you should look through the reviews and check out the exercises and make sure you understand everything. Feel free to ask questions, and as always, I will be sending the answers to the exercises. So thank you all for joining. Have a great rest of your weekend, and get excited for winter break. So good night, guys.